Good afternoon for those that are in the session. We thank you for coming today. Before we begin, please, as a reminder, fill out the attendance survey. I have added the link in the chat. There's some additional links that we're going to get to in a second, but if you could just do the attendance survey first, we will explain the other links shortly. So while you all are filling out that attendance survey, I will begin with the bio of Ascii Codes. She is an associate professor at TSYS School of Computer Science at Columbus State University. She teaches courses in programming and security. Her research focuses on cybersecurity and cryptography. She is an ardent supporter of computer science for all and equipping the teachers with the right tools so that they can effectively teach the younger generation the skills of the century. So without further ado, Ascii Codes.
Thank you, Terry, very much. Hello, everyone. Welcome to this session. So today I'd like to present to you a cute little activity, a fun little activity that you can use hopefully in your classes. I say little, but it's a research area in itself. But there are some parts that are very easy to integrate into computer science classes or even math classes. So here I have 2 links posted for you in the chat, and one of them is for this presentation, the slides for the presentation. It's the folder link, the shared folder link. It has the presentation slides, and it has some of the files that I will be using during my presentation. And if you want to follow along with me and do some hands-on activities during the session, then I will ask you to download this program called steghide.exe. It's a zip file at this link, and it's available for Windows and Linux machines, unfortunately not available for Mac. And it's a small file. It doesn't take too long to download, and then you unzip the file, then you have the steghide.exe program that you can use. So I'm going to talk to you about information hiding using least significant bit steganography. Okay, I've already shared this and this, and I'd like you to do one more thing for me, and that is I would like to know my audience when I start a talk. So I have this basic information that I'd like to get from you about your classes. So if you can fill in this survey for me, I'll appreciate that. Let me in the meantime, go here and maybe look at the results with you. Okay, so the responses are coming in, and I'm sharing it with you. So I see that we have lots of teachers, as I was expecting. And most of our teachers are high school teachers, and some of them are middle school teachers. I don't see any elementary school teachers. The session was intended for middle and high school teachers. So I see that there are actually some of you who teach steganography in your classes and in detail, and some of you talk about it maybe briefly, and most of you don't really cover steganography. How data is stored, of course, many of you cover it, and some of you in detail, and some of you in less detail. And then information security, many of you briefly covered in class. It's a big topic, so to cover it in detail, I think you need to have a separate cybersecurity class or information security class. So thank you so much for your responses. Now I will go back to my presentation and start telling you about steganography. So steganography, the word comes from the Greek steganos plus graphe, which means covered writing. And it is the technique of hiding secret data within an unsuspected medium in order to avoid detection. So steganography, the digital steganography is a new thing, but hiding information in various mediums has been around from a long time ago. For example, in the very old days, this method of shaving the head of the messenger, tattooing the message on the head of the person, and then growing the hair back so that the message was hidden was a method of hiding the data. So that would be steganography used there. Or invisible ink is another way of steganography. Or, for example, microdots are where you have a lot of information written on these very small pieces, and then they are in a way folded to have these dots where you expand it, you can see lots of information. So those are some non-digital examples of steganography. Here's another example. Can you tell what this message says? I mean, you can read it. It sounds like a meaningful statement around the wartime. This makes sense. It is in this resource here by Gary Kessler. It stated that this was a message that was sent during the World War I between two German embassies. So there is actually a hidden message in this one, and in order to get the hidden message, you look at the first letters of the words in the message. So Pershing sails from NY June 1st was the message that was hidden in this longer message. And I'm sure many of you have, when you were younger, did this kind of thing. Kids love, these kinds of fun games where you hide stuff and then you communicate secretly with your friends. So I think this would be a good activity for pretty much any grade, then coming up with their own way of steganography. Here's one thing I'd like to explain. Encryption is a more common technique used, and we hear about encryption a lot. I just wanted to emphasize the difference between encryption and steganography. So in encryption, we transform the secret so that it is unrecognizable. And in order to get the original message, the real message, you need a key. If you don't have the key, then you cannot extract the message. Of course, this is for, I guess, strong encryptions. For example, Caesar Cipher is an encryption method that was, again, used in the past by Caesar. And in this one, what you do is you shift each letter of your message by 3. So, for example, attack becomes this unrecognizable, illegible word. And if you know that 3 is used to shift the letters, then you know how to get the attack back. The goal in steganography is slightly different. Steganography hides the existence of the secret. So someone looking at the messages going back and forth between two people doesn't even know that they are sending anything secret. So that's the distinction between encryption and steganography. So how can we hide secrets in digital mediums? So here's a question I have for you. These are two different files, the sunflower.jpg and then message.jpg. Do you see any difference in these files? They look very much the same, and we will come back to this picture later at the end of the talk. In order to talk about how we can hide data in digital mediums, we need to first understand how data is stored on computers. And I think all of us know that it is stored in bits on a computer, and a bit is really representing a 0 or a 1 stage, on or off stage. That comes from the physical structure of the computer, where you have you can think of it as a switch. So turning on the switch is 1 and off is 0. And when we say data, data can be text, image, sound, video, application file, or some executable file. So there are various types of data on the computer. And we need to understand the properties of different data files when we want to embed data in them, secret data in them. So I'm going to concentrate on text data for a little bit. And so this is data that consists of our usual characters, our letters, digits, punctuation, not only these, but all those other characters that you have on your keyboard. So how is this represented on the computer? I guess the very first encoding of the characters on the computer was in the American Standard Code for Information Interchange. In this, 8 bits are used to represent each character, 8 bits. For example, the small letter A is represented by these bits, 0, 1, 1, 0, 0, 0, 0, 1. So that represents A. When the monitor sees these, then it knows to display A. So that's at a very high level. So if you go to this link, you can see that you have the letter and then the Ascii code. This is a little different from your usual Ascii tables. It is made more for the layperson who knows the alphabet, A to Z, and then uppercase letters A to Z. So the Ascii code is 97, and it is this number in binary. 97 or 97 is the binary code for it, and this is the corresponding binary number. So, like I said, there are more than those in an Ascii table. So these are all the, first of all, with the 8 bits, you can actually represent 255 different characters. Here you see the 128 of them. These are the ones that we have the characters that are on our keyboards. Like starting here, space is 32, and then exclamations is 33, and then you can see the rest of the characters and the codes that correspond to them. And we are going to come to this in a little bit later. Okay, so for example, let's say I have the word cat, and I want to write its Ascii code. So I need to find C. C has the code 99, and the binary that corresponds to this is this number. And the little a is 97, and that's the binary code. And then T is 116, and it's the code. So the cat is represented using these 24 bits on the computer. Here, I guess at certain points in my presentation, I'm going to sort of diverge to some other topics and just mention you how you can maybe extend your class if you have time, or if they are related to some other topics, how you can extend your the topic to some other areas, like encoding of these characters. There are other encodings. You can remind students that, for example, these are not enough to represent all possible languages. There are languages that have very different character sets. So this is only 128 characters, or if you use the whole ASCII, it's only 256 characters that you can represent. So in order to represent other, like to be able to communicate in other languages as well, we have other codes. We have Unicode and some other formats that makes it easier to work with when you're programming. I think, I guess in terms of diversity, it's good to note that even technology needs to be considered. It needs to take into account the diversity of the world. Okay, here is a message I have for you. So this message, would you delete this message? What does this look like to you? It looks like spam, exactly. Thank you, Mark. Yeah, it looks like a spam message, and you may just delete it if you don't know. There is indeed a message hidden in it, and this is, I put this as an example of steganography. This is an interesting one. I don't really know how to extract it by hand. Let me come back to this later. But it was obtained using this site, spammimic.com, and the goal of this site is you give it a message that you want to encode in a spam message, and it creates for you a spam message. And then if you get back to this site and want and decode that message, then you will see what it says. So let me try what I have here. All right. So decode. And then if I hit decode here, you'll see that it says meet at 7 p.m. So from that spam, you can actually extract this message if you know that it has some data hidden in it, and if you know that it was created using whatever algorithm that this site is using. Like I said, I'm not sure what algorithm they use, but here is another divergence from what we are covering. So what you can do is, for example, in this site, you can try to break this. So at what point does this break? So let's say if I put some spaces in here, is it going to break? Is it going to still decode to the same thing, or is it going to give me something different? So it did decode. So let me go back and place this in here, and maybe I will add somewhere in the middle some characters, additional characters. So I'm trying to break the system now. And if I do this, now I get something that cannot be decoded. So this may be a way to figure out, I mean, then it is done in a much more systematic way. It can be a way to understand what algorithm this site uses to create the spam. Another thing I wanted to show you here was this Ascii code. Oh, sorry. So this, not the Ascii code, sorry, but this file that I have. So I created a file called spam.txt, and then I put this spam message in there, and then I opened this file in what we call a hex viewer or a hex editor. So here I have the link for a freely available hex editor. It's called Hex Workshop. So you open the file, and here you see, dear friend, this letter was specially selected to be sent to you, and so on. And it shows you what bits are stored in the computer for this data. So for example, D is 44. Well, if you look at the Ascii code, D is not, capital D is not 44. What is shown in here is the hexadecimal equivalent of that Ascii code. So it is written in hexadecimal. I think this can be a good way of, a good example of abstraction. I know one of the big ideas in, not big ideas, but one of the, I guess, topics in APCSP is abstraction. So here you can actually see the letters, the bits abstracted in letters, and then you can see the bits abstracted in hexadecimal values. I included here how hexadecimal and decimal conversion works, and how binary and decimal conversion works, but I'm assuming that most of you are probably familiar with these conversions. So please let me know if you want me to go over these through the chat. I'm going to just look quickly. If there is anyone who needs me to go through these conversions, because I'm going to use at least the binary decimal conversion later again. Okay. Okay, great. So let's go on then. So we extracted the message from that span, and we got meet at 7. Now I'd like to ask if you have any questions. I have included these slides in my presentation just to remind myself that you may have questions, because I tend to get carried away with what I'm talking about. So do you have any questions? I should also note that please feel free to ask questions when I'm talking as well through the chat. And our wonderful Terry is going to let me know about the questions, and I'll be happy to answer them as we go along.
Absolutely, I'm here for you.
Thank you. Okay, so I don't see any questions. So now then I'm going to continue with my presentation. So now we looked at the text data, how the data is stored on the computer, and we just looked at one encoding. Again, remember there are many different encodings out there. So how is an image stored on the computer? An image is stored as pixels, short for picture elements, and pixels have attributes that define them. There are different kinds of images, I guess 3 main types of images. There are binary images. These are 2 colors. They consist of 2 colors. And in order to represent a binary image, you need 1 bit per pixel. I put here representing black or white, and I forgot to change it. I think it's really not black or white, but it's background and foreground. So it doesn't have to be black and white. It can be red and blue. But you need to specify whether it's going to be in the background or in the foreground. So that is your binary images. And then you have your grayscale images that are black to white, and you have shades of gray in between. And usually you need to specify the brightness of the pixel, and usually 8 bits is used to specify that. And then there is color images. And color images, there is a lot more ways of storing color images. So there's, for example, red, green, blue. These are the 3 primary colors. They're called additive colors. And you can combine them at different intensities to get other colors. So red, green, blue is one of the color schemes that is used. there is hue, saturation value, there is hue, saturation, lightness, there is cyan, magenta, yellow, and there are others. And there is this really nice site where you actually see all these different color schemes, and you can see the effect of changing the components by sliding these bars. So for example, for the RGB, well, here, this is what you're viewing. There's a background, and then there is the text inside. So I'm going to make changes on the background. So I'm changing the background to, I'm including less red in the background. So the red component is 0. I have some blue and some green, and so I get this color. If you make it, let's say, just red and green and no blue, you get yellow. Again, these are things that I guess we had fun with when we were little kids. I still really like, how colors interact with each other. So, and you can look at these other ones here as well. Again, as a side note, I think this is a great, when you're teaching maybe functions and math or dependent variables and independent variables, you can make changes on one of these components, and you can look at how the others are sliding, and you may be able to say, okay, this one and this one are the same. They're not, they always follow each other. When I make changes on one, the other changes the same way, and so on. So I really like this site, but we are not going to go into details of any of these color schemes except for the RGB. So I'll go back to the presentation, and I'll talk about the 24-bit RGB color scheme. So the 24-bit RGB color scheme is where 8 bits are reserved for each color component. So 8 bits for red, 8 bits for green, and 8 bits for blue. So let's say I have an image that has 4 pixels on it. I have the red pixel, the black pixel, the yellow pixel, and the blue pixel. So, and let's say in this red one, the intensity of red is at its highest, and there's no other color in it. So it will be represented by all ones. And then for the red component, zeros, all zeros for the green component, and all zeros for the blue component. So it will be represented by 25500, 25500. So you have 8 bits. The smaller number you can represent is 0. The highest number you can represent is 255. So here it's the highest intensity of red. And here you have 0. So this is the red, green, and the blue for the red pixel. And for the black pixel here, there's no color, it's all zeros. In the yellow pixel here, you have the red and green, and they are at their fullest intensities. So, and there's no blue, so 255, 205, 0, 5, and 0, and you can tell how the red one works, how the blue one is. Now, if you go to this side, this is similar to the other one, but this is just for RGB. And here, I'd like you to notice something that, if I change here, let's say I have this color, okay? So I have this is at 255. And I'm making some changes here. So I'm going to move the green component to maybe, okay. So this is what I have, and I want to move the component to 106. The color changes, but it's not that easy to detect the change with our eyes. And this is what least significant bit steganography uses. It is about making changes in the image in a way that the human eye cannot detect it. So let's go back to our presentation. And let's say I'm going to hide the word cat in this image of mine. So cat, if you go back to their Ascii code, C is represented by these bits, A by these bits, and T by these bits. So I have 24 bits in total that I want to hide. So what I do is, for my first, I start with the bits in my message, and then I look at the red, green, blue components, and I forget about the last two bits in each of them, and I replace those bits by my hidden message, the bits of my hidden message. So 0, 1, 1, 0, 0, 0, and then 1, 1, 1, and then 0, 1, and then 1, 0, 0, 0, 0, 1, 0, 1, and the T is there as well. So I have now changed the image. So instead of 255.00, as I had in my original image, now I have 253.20. And then instead of all zeros, I have 312, and so on. So I have changed the image, but when you look at the image, but when you look at the image, we can't really see any change. And the reason, because we cannot see any changes, because the changes we have made are so subtle. So what is the maximum difference between values of an attribute here, between the original image and the stego image? If I'm changing only the two least significant bits, what's the maximum change I'm making on an attribute? 3, right. The highest I'm changing is if I hit 0, 0 here, and if I made it 1, 1, that would be like adding 3. Or the other way, if I hit 1, 1, and then I changed it to 0, that would be like subtracting 3. That's the most drastic change that I will cause. And if you go back here, and if you just change, for example, this by 3, you don't really detect any change in the color as a human. Yeah, if you ask the computer, if you compare the two files, then they are going to be different. They're going to end up being two different files, but for human eye, this is not the case. So how many bits did we hide? We were able to hide 24 bits in 4 pixels. It's actually a lot of information that we can hide. Sorry. And let me ask you this question. Do you think the file, the size of the file has changed with this operation? Did we make anything that will change the size of the file? Oh, why did I choose red, black, yellow, and blue? Well, I guess I wanted, when I embed the image, I just wanted the difference, the numbers to be easily remembered from one to the other. Okay, so the file size shouldn't change, right? Because all we did is we replaced the 2 bits with our new 2 bits, and we didn't add any bits or take out any bits from the file. So it still has the same number of bits. Okay, any questions on this? Okay, so, oh, I see. Why not red, green, and blue? I just wanted to show that, there is also possibility of mixing the two. So I mixed 2 of them. Just for a variety. Okay, so where is steganography used? Steganography, as I said, the difference of steganography from cryptography or encryption is that it hides the very existence of the message.
There's another question, yeah.
Okay, let me see. So the image, so when first of all, we have to understand that the receiver is expecting this. The receiver knows that they're going to get this image and there's going to be some hidden data in it. And they are going to know what kind of algorithm is used to embed that data in the file. So this is the assumption. We have two people, they are communicating and they want to hide their communication. And they agree on some algorithm, and then one of them embeds the data and the other one gets it and is able to extract it. So the RGB value of the color, that is already stored in the system. I mean, on the computer. That is how the file is stored, those RGB values. And I'm actually going to show you a Python example that shows you how to extract those RGB from a JPEG file. Does that answer your question, Ilana? You're welcome. And then so every 4 bits. Okay, so it really depends. Here I use the least 2 significant bits. If I were to use less than 2, if I were to use only 1 significant bit, only the least significant bit, then I would be able to embed or hide only how many are there? 12. I would be able to store only 12 bits or hide only 12 bits in here, and that doesn't even make 2 characters, right? It really depends on what the algorithm is using. You can use 3 bits at each of these attributes. So with 3, now you're able to store 36 bits. And even though we talk about characters, but it's not necessarily always characters that are hidden in images or in other mediums. You can hide a picture in a picture. You can hide a picture in an audio file. You can hide in video files. There are techniques to do those. Okay, so where do we apply steganography? Which industry uses it? Okay, so it is actually, I think maybe the profession that deals with steganography the most could be digital forensics people, because a lot of the times, some ill-intentioned people may use this kind of tool to hide their communications. So let's say an attacker wants to hide some executable file, some malware in an image. So you get the image and you download it, and if they know or let me explain it this way. So let's say we have an attacker who wants to get into others' computers, and what they do first is they send you an image. It's an innocent-looking image. Maybe it's an image of a flower that you really like, and so you download it on your computer, and then somehow they get into your computer, and they know that that you have downloaded this on your computer, or they check if it is there, and then they have a program that can extract this to your computer, and it turns out that this is a malware, a virus that can have your computer turn into a bot, for example. Or some other, not exactly steganography, but related to the similar idea is, for example, watermark. Watermarks are, you can put watermarks, digital watermarks on, let's say, artwork, and so only you can know how to extract the message or the watermark. It proves that it actually is your work. Somebody else cannot just take it and claim that it's their work. So there are some, and there is, for example, back about, I guess, 6, 7 years ago, there was this uprising in Egypt, and there was a lot of oppression of communications with the outer world from Egypt. And what people did is they sent innocent-looking messages to the world, and then they were able to share what was going on actually in the country using steganography. Okay, so let me see this question too. You could just use more pixels. Yes, sure. I mean, 4-pixel image, I don't know. I mean, I just made this up. It's not really 4-pixel image, but it's just made up. But normally, I mean, pictures have a lot more pixels in them. And you can actually see one of them in this Python code. So I did not want to make this session about programming. That I did not want to make it to assume that the participants have no Python programming, but I saw that there were many of you who were actually using Python at another session, so I decided to include some code that you can use in order to hide data in an image. So those of you who are familiar with Python, this shouldn't really be very difficult to follow. And I have here the code embed.py that you can use. If there's interest, I can demonstrate for you how this works. Just please let me know. But the idea is in Python, there's a library where you import the image library from. And then let's say, and this is very, I guess this is a very simple code. It's written in a very short amount of time. Normally, I mean, there's a lot that goes into it, but I think this is good enough to demonstrate to your students and maybe have them work on it and do some different things. So let's say this is cat, the secret data. You open the cover.jpg. I have a file called cover.jpg that I stored in this shared folder here, but you can use any file. It has to be, I mean, it shouldn't be an SVG file. The common like bitmap or PNG, I think they should work, but not some of the newer formats. Okay, so you open this file and you call it image. You get the width and height. So if you multiply the width and height, that's how many pixels you have. So you can actually print that information on the screen, and then you convert it to its RGB format. So with this, you have a image that is stored in the RGB format. So then you go through the x-axis and through the y-axis of your image, and you get the pixel. That is, when I say that, you get the RGB values, and each of them is a list. And you go through those RGB values, and you embed your data. The data is these bits here. So you embed it, and there's this and or operation that you use, and essentially gets the last bit to be 0, and or sets the first bit or the last bit to the data bit. I'm sorry for the typos. I think really fast. And this only hides the data in the least significant bit. It uses only 1 bit. And then, oops. And then it puts the pixel in your image. And finally, you can, if I can get this, let me do this. Okay, maybe I'll just show it here. At the end, whatever changes you have made, you store it in a new file. So I call it stego.jpg. So let me go in, and here, this is the code that I have posted here, posted there. And sorry, it's not that code. Let's see now. So here I have the embed code, and this is my cover image. So this is the cover that I have, and if I run this program, then here you will see that I have a new file created. It is the stego.jpg, and you can see that it doesn't look any different from this other cover.jpg that I have. So they are the same. And if you are teaching programming, you know, this is a great way for students to have some fun. So for example, you can say, so what happens if I make a much larger data and if I impact more of the image? So in order to demonstrate that, I have created this other file. Just make some changes. So here I have the data, but what I do is I append to the data itself several times. So I make the data much longer. So these bits repeat, I don't know, hundreds of times, maybe 1,000 times, because I have a for loop here. And then at the end, instead of changing only the last bit, I also make a change in the first bit. So this is also different from what I have posted for you. So I make this change. So I'm impacting, or I'm making a change in the first bit of the attribute as well. So now, and I'm going to store this as stego2.jpg, and I'm going to have this open here, so you can see the file being created. Okay, so here you have the stego2.jpg, and now if you look at this file, it is different from the others because now we have impacted the higher significance, the highest bits, high significance bits of the file, and we did it on a lot more attributes. The first one is just, it is just 24 bits that you won't, even if you take away this, you won't make your data bigger, you won't really see much change because it's only changing just 24 bits of the file. But the file is actually a lot bigger. Actually, if I uncomment this print statement, you can see that you can see the size of the image. So it says 600 by 386 image. So it's 600 times, I guess, about 200,000. 240,000 pixels is how many pixels there are in this picture.
There's a question from Stephen on how you would extract it.
Okay, I haven't written the extract program. Like I said, I thought about this after I looked at some of the presentations yesterday where people said that they actually were using Python. So I thought it would be good to include this. But to extract it, you would do the same thing. You would open the image, you would get the RGB values, and then I guess you would then you don't really need the cover image anymore. You need to understand that you don't use the cover image. You just have the stego image, and you are going to get the very last bit of each of the attributes. You're going to get the very last bit of each of the attributes, and then you can print them, or you can take them 8 by 8 and find their ASCII characters if you have embedded a text image. I mean, a text data. You can do a lot of things if you use Python programming or any other programming, really. I think they all have libraries for image processing. So if I get the time, I actually enjoyed working on that one. So I will make it available on this shared folder. Okay. Any questions? Okay, then I will move on to our next part. And this is a software that you don't need to do any programming in this one. This is a software that is used, that is implemented for, I guess, educational steganography, I should say. It does have these significant fits, but it's not immediate. That's why I said the one that I have is very simplistic. It doesn't really have any mechanisms to make it stronger, but this one is a little different, and I'll tell about how it's different in a little bit. If you want to follow along with me, you should download this software from the site, and here, and then it will be a zip file. You extract it, and you will have steghide.exe. When you unzip it, please make sure that you remember where you stored it, because we will need to actually go to command line and work from there. So in this is a command line tool. So like I said, we will have to use command line, and these are essentially the two basic images that you have. Not images, basic commands that you have. So you use steghide, and then -- embed, and then -ef for the embed file. That's the secret file you want to hide. And then you will have a cover file that you will indicate by the -cf option. And then you will have -sf for the stego file, the output file that you will create. You can ignore the -sf, the stego file, but then it will write onto your cover file. So you need to be careful about that. And then when extracting, like I said, you only need the stego file, and then you can define what file you want to extract it to. Or if you don't specify any file, it is going to actually figure out what the name of the file is. So the steghide algorithm, it hides the name of the file as part of the hidden data in the file. And not only the name of the file, but also some metadata about the file, like the size of the file, other things about the file. They're all included as part of the data. So are you ready for a demonstration? So these are the two files that I have in the shared folder, sunflower.jpg. Oh, I guess I didn't put that, but you don't really need that. That's, I guess, why I didn't put it, because the message is in the second one, in the message.jpg file. So I see that Steven says he's ready for the demonstration. I hope more of you are able to follow. Please write in the chat any questions you have. I'd like to make sure that you're getting something out of it. So in order to go to command prompt, all I do is write cmd at the start menu, and I get to the command prompt. Would you like me to show you how you download and then extract the steghide, or are you good with that?
And just a reminder, this is for PC only, correct? No, not Mac users?
And Linux.
And Linux. Okay.
Maybe for the sake of time, I will go ahead and do this. Okay, yes, unfortunately, I could not find a similar software that works for Macs. So I've heard about Silent Eye and Outguess. I think they would work too, but you will not be able to extract the files that I have put here for you using that, because the algorithm they use is probably different. So I have here two things that I want you to actually extract: the message.jpg and the mystery.jpg. Both of these files have some hidden messages in them, and I'd like you to extract it if you have installed or downloaded the software. But if you have another software for a Mac, they will not be able to extract the message because their algorithm is probably different, unless the steghide people made it. So is anybody giving a try to extracting the messages in this one? And again, the commands that you will use are, you will have to go into the folder where you unzip the steghide.exe, and then you will write steghide, and then, oh, to extract, I'm sorry, I have the wrong thing here. This should be not embed, but extract. I'm very sorry about that. So one is for embedding, the other is for extracting. Okay, shall I wait a little bit to see if you will be able to figure out what the secrets are in those two files, the message.jpg and mystery.jpg? These are in the shared folder. I'll just give you some time for those of you who are working on it. Maybe some of you are working on it. So what I will do is I'll show you here what you would do to download it. So under download here, so I have a Windows machine. So I will download it, and it will say it will download in a little bit. Okay, so you just have to wait a little bit. So I have this that I'm saving, and then I'll go to the folder where it is saved. It's under downloads. So I'm gonna extract it. So let me just extract it here under the downloads. So now I have this created, this folder created, and under here I have the steghide, and I have these files that come with the application, and steghide.exe is one of them. So in order to use this, you either have to make sure that this directory is in your path, so you can run it from anywhere on your computer, or you have to go into this particular folder and run it. So, for example, for me, what I would need to do is I would need to go to command line, so as I did before, and then I would have to go under downloads. So you do that by CD downloads, and then you can look at what I have here, but I know that the name of it is steghide, and then another steghide. And so I have these files in here. dir is how you list the content of the directory or folders in Windows. So I use dir, and I have these. So from here, if I say steghide, you will see that it's expecting me to give it some options. It doesn't know what to do just with that command. So in order to in order to use it, I need to put my file in here. So that's what I'm going to do. I'm going to go to my folder. So I have, these are the two that I have, message.jpg and mystery.jpg. Let me copy them and let me go under downloads, under here, and let me paste them in here. So this folder is a brand new folder. It doesn't know anything about my secret messages that I hid in those, or secret messages that I embedded in these pictures. So let me first make sure that I have those in here. Okay, so I have the message.jpg, I have the mystery.jpg. So let's go with the message.jpg first. So, and when the file is created, it is going to, you're going to see it in this folder, the steghide folder. So let me extract it. So I'll just use some convenience in here. So I want to extract what is in the message.jpg file. And I'm going to put it in, let's say, extracted. Or, yeah, extracted. And I'm not going to specify what kind of file it is because I don't know maybe at this point what type of file it is. So I'm just going to run this. And oh, it's going to ask for a passphrase. Steghide automatically encrypts things and uses a passphrase. So I used hello. And sorry, I should have noted this. So hello is the passphrase. This is something with the steghide software that they have in place. They always ask you for a passphrase. So now it has actually extracted it, and I should have a file called extracted. So this is the file extracted. Now I'm going to go to this folder, and I'm going to refresh this and see if I have my extracted in here. And yes, it is in here. And it's interesting. Sometimes Windows recognizes what type of file it is, but let's rename this as .jpg. You know, or better, let me show you one more thing before I show you what it is. So I made this command and I specified here a file name for the extraction, for the extracted file. Let's say I don't want to do that. I'm just going to extract however it is stored in this message.jpg. So what will happen is it says this extracted data to secrets.jpg. So this was the original file, the name of the original file. So steghide incorporates this metadata about the file to the embedding process. So even if you don't specify what the name of the file is, what the name of the file is, it will be able to figure it out. And again, you don't have to know the name of the file to be extracted to. You can use that XF option in order to write the name of in order to give the file a new name, because sometimes you don't want to overwrite what you have and things like that. So you can do that. But let's now go to that secrets.jpg and see what the image was. So here's the secrets.jpg, and it was a cat. Oh, the two files that I downloaded into steghide were this message.jpg, that's the one I use now, and then there's another one, mystery.jpg. All you need in order to extract is these files. I mean, this one of the files, just to experiment with it. So that was what was hidden in message.jpg. sorry, Stefan, I just want to understand your question correctly. So in the steghide folder, most of these files, they came from the zipped file, right? When I unzipped the file, it created this steghide and it put everything in here. Most of these files, other than these images, are the files that are part of the application. They come from steghide site. The only file that I copied here was this one, message.jpg, and I just showed you how you can extract the hidden message in it. And then there's another one, this I was going to assign for you for activity. So you can try, you can give it a shot, see if you can recover the message in this one. And once you have the software, you can create your own files. You can hide an image in an image, audio in an image. You can hide text in an image. You can really hide anything, any digital data in it, as long as you have the zeros and ones.
Okay, we have about 7 minutes, so just wanted to keep you updated.
Thank you very much. So I hope that was helpful. I will leave the other file to you to figure out what it has in it. So we figured out that there was a cat in this message.jpg that was hidden. One thing I guess I wanted to show you was that if I go back to my folder, if you look at the sizes of the files, you will see that if you look at sunflower.jpg, message.jpg, mystery.jpg, they are all of the same size, because we didn't really make any, I mean, steghide doesn't really make any changes in the number of bits. The file size stays the same. And actually, that's sort of important in steganography, because the idea is you want to hide the existence of the message. So a lot of the times, pictures or messages are hidden in these common cute pictures, and there are tools that can quickly check if the sizes of the files are the same or not. Those are tools for, I guess, steg analysis. So there is an area of research that's called steg analysis. Oops, it's a typo. The goal of steg analysis is, first of all, to identify suspected packages. So if whether a medium has some hidden message in it or not. So if, for example, you increase the image size, then it will look very suspicious. So so you don't want to do that when you have a steganographic technique. And then, if possible, once you figure out that it has indeed some secret message, recovering that payload, that message in the medium. So this is steg analysis, and it uses statistical analysis and machine learning. Those are the two main tools used in steg analysis. For example, the least significant bit steganography is not a strong method for hiding data. There are some statistical analysis that will tell you what the ratio of bits should be based on the higher order bits and so on. So it's not very hard to detect least significant bits, least significant bits hidden data. Now, how steghide works, it does have some least significant bit manipulation at the end, but it tries to hide those statistical properties that steg analysis uses. And here I have the description of how it's done, but I don't think it is that important. It's important to, I think, emphasize that when you use steganography, the other side has to know what technique you use exactly, so that they can recover the message back. And finally, I have, in the last, I guess, 3 or 4 minutes, I have another survey for you where I ask you how, if and how you will use this material or parts of this material in your courses. So let me, I thought I put the link there, but I did not. So let me do this. So if you can share with us maybe very quickly if or how you could use this material. So we could share it. You can so everybody sees. I guess it's an opportunity for us to learn from each other. But I'm sorry that there is so little time for this.
Are there any other questions for Yashim?
Okay, that's great. The Cipher is fun. Oh yeah, those competitions, capture the flags. We have done it. I mean, our students have participated in various capture the flag competitions. It's a lot. It's very motivating and a lot of fun. Okay. Yeah, absolutely. It's you know, and then the convergence hexadecimal binary code. This is a great example, and for example, the hex editor is a very easy tool to use just for this basic type of thing, just to show them these are the bits that are stored for this file. That's very powerful. I mean, I've seen it even with my students. You know, I teach at the university, but a lot of my students, even by the time they get to my forensics class, have not really seen the files, the zeros and ones of the file. So they like that. Thank you so much, Ian, and thank you to all. It was great to have you, and thank you for participating. I hope you got something that you can use in your classes. Oh, so you teach color systems. That's nice. You're very welcome, Don. You're very welcome, all. And please feel free to email me to ask any questions. I should provide my email address. I think it is in my profile, but.
Thanks everyone again for joining us. Did you need anything from me before we leave?
No, I'm good. Thank you very much.
You're very welcome. We will pass on any of the data from the surveys to you once the event is over this week. Okay?
Okay.
You're very welcome. You take care. Be safe.